today I want to talk about moving fast and making things. We've already heard a little bit about services and other things that you end up doing when you reach a point where your application is too large. It has become unwieldy. And a lot of people in the community are looking for ways to solve large software. How do we deal with a Rails app when it becomes really huge? What can unit testing, what can object-oriented design, what can other programming languages entirely offer us when we get to the point where we have large teams, large software, etc. So I've been thinking about that problem, and I think that in addition to things we can do directly with the code, there's some ideas we can leverage to sort of come at that problem from all directions instead of just trying to solve it with just unit tests or just design techniques. So part of the problem with large applications is because they become time intensive. And time is the one thing that none of us can produce, none of us can buy, and none of us have enough of. The real bummer about time is that it is broken by design. It only ever goes forward. You can only spend it. You can't get any more of it. And so what we have to do is figure out how we can do more with what time we do have. How can we make more programs or get more done with our teammates or make more product in any given amount of time? And we also need to figure out how can we do more of the right things with our time. So working smarter with our time is in part about like not checking Facebook all the time, but also about saying, is this thing that I'm doing right now high enough value for me to keep doing it? Is maintaining a test suite a high value thing? Am I getting benefit out of it? Or maybe I should stop maintaining this part of the test suite or this part of the code, whatever. So we want to move fast, and part of that is like just feeling like we're getting something done, feeling like we have busy hands, that we're not running in sand. But part of that, the real part of it is making more stuff, shipping more code, shipping more product, creating more product, even if that doesn't mean shipping code, maybe deploying documentation or writing documentation for other programmers. There's some unit of work, something that is useful about what you do any given day or any given hour to make progress. So we want to move fast and make more of these things. Another part of moving fast is to reduce huge challenges to things that we know how to tackle and that we could actually accomplish in a reasonable amount of time. I'm sure all of you work on some project or some application, probably on a daily basis, and there are pet projects that you would love to take on. Some feature you would love to add, some refactoring you would like to do, some performance bottleneck you would like to eliminate. But it's such a big application or such a big problem for your product that you don't know how to do that in a reasonable amount of time. You think that it would take weeks or months to accomplish it. And so you just can't end up doing it because you can't justify that. So part of moving fast is to figure out how to reduce those big challenges into smaller things that you could actually tackle now and get some benefit out of. And like I alluded to before, moving fast is also about doing the right things. So definitely, if you're trying to meet a deadline or ship some code, you probably shouldn't be checking Twitter or just chatting with people or looking at funny GIFs. But also, you shouldn't be fighting your tools. You shouldn't be fighting the code. You shouldn't be wondering, what does this code do? Why is this code here? Why do I have this process in my team where after I finish a feature, I have to squash all of the commits down to one commit so I can cherry pick it? Why am I doing these things? Is that the right thing to be doing with my time, which I cannot get any more of? So we also want to make things. We need to discover and solve the risks. Part of the challenge of building software is that there's all sorts of uncertainties. We don't know how long it will take. We don't know what problems might be lurking, what complexities might be lurking. We don't know often where the code is that is going to leave us confused and wondering why it's there. So we need to discover these risks and solve them. We solve them by identifying them and then figuring out, okay, well, we can work around this, or we should schedule time to really solve this problem correctly, or we figure out, hey, I can just not solve this problem at all. Someone else has solved storing credit cards. I'll let them handle it. I won't go through all this PCI compliance crap, for example. We want to make things. We want to add features and kill bugs. This is what probably everyone wants you to do in your job as a software developer. Make this thing do more things, make it not break so often, make it faster, make it better. We want to make things faster. We want to eliminate bottlenecks, make things scale better. And we also want to facilitate change. This is my way. Facilitate change, I think, is a better way of saying, I need to improve this code. There's code that I need to refactor, or code that no one understands, or it's hard for us to change. It's resisting change. So I want to change this code, spend some time changing code so that I can facilitate further change down the line. Changing is what software does. If a problem is not changing all the time, then you can just make hardware for it, or you can just ship it and be done. But most of us probably work on software that's been around for a long time, is profitable, makes money, but needs to do things differently. And so we need to make more things by facilitating change. So we want to move fast and make things. And I think the crux of the biscuit, the core problem with people, with monorails and large businesses, large teams, is that big things are an organism and they resist change. And so that becomes our enemy. These big things have wants and needs. A large software application wants you to spend a lot of time setting it up. Oracle is not trivial to get set up, for example. A large code base, if you work on a monorail, you probably know of some part of the application that defies comprehension. Every time you modify that, you have to sit there, look at the code, look at the data, load it all into your head, and then figure out how to actually make the change you wanted to. Large teams beget large processes, which have their own sorts of wants and needs. Once you have a large team, then you start to need office managers and HR and payroll companies. So as things grow, they acquire more desires. They become this organism that has its own wants and needs as though it was a human. Big things beget other things, big things. So if you use Oracle, then it's likely that someone's going to be like, hey, why don't we just use PeopleSoft too? And so now you have two huge, terrible things. Like I said, a big team is going to, a large monolithic software team, if you have 20 people, at some point someone's going to botch a deploy, and then you're going to say, oh, we can never make this happen again. What rule can we put in place to make this never happen again? And then you'll have some stupid rule that's hanging around for a long time. So big things are a problem because they want to make other big things. And like I said, big things resist change. It's just hard to say, okay, I'm going to take this large rock, this large metaphorical rock, and move it. You have to be really strong or have a really good plan and a lot of people to move that rock. Whereas if it was just 10 smaller rocks, then it would be easy in theory, right? So what we want to do, the place we want to be, we want to set the goal to have a lot of small things that are disconnected, easy to reason about, and that are our friends. Small things are great because they don't overwhelm us. You don't stare into a small thing and have it stare back at you. You can look at a small piece of code and say, I can see what this is doing. I can see its interactions with other things. I can see that this is where I might want to change it right away. If we're a small team and we only have 4 rules about how deploys work, or 1 rule about how a deploy works, or it's all automated, then that's easier to work with, easier to understand. We don't get so overwhelmed that we are tempted to go check our email or check our Twitter or go complain to one of our coworkers. Small things are loosely held. We don't get precious about small things. If I hand you a golf pencil, then you're likely to be like, okay, I'll write something down and then throw it away because it's just a golf pencil. There's like 20 trillion in the world and they cost like a fraction of a cent. If I hand you a beautiful pen, then you might keep that around because it's a beautiful pen and I gave it to you. You appreciate that, hopefully. So if we have more small things, then we don't have to be so precious about them and they don't acquire all these wants and needs and desires. And small things have to adapt or else they disappear. So if you have a small piece of code, even if it's not terribly well written, you can look at it and say, okay, I can understand where I need to make this change. I'll make this change. Or you want to add a feature to it, you can say, okay, I can add a feature, make this maybe 10% bigger, and it won't end up with a huge morass of code. I can do that quickly. If you have a small thing and it's just utterly terrible, you can just say, okay, it would take me a week to change this or a week to rewrite it. I'll just rewrite it. And that's maybe not a bad decision. So small things are easier to reason about and easier to work with. So if we can get to the point where we have small things loosely joined, to use a metaphor, then we can then we're not faced with the problems that these monorail, large applications, large teams, et cetera, present to us. So I think the way we get to having these small things is that we have to resist having large software. And then and that helps us go faster. So we get to large software by divide and conquer. We have to look at our applications just like Yammer has, just like Living Social does, GitHub does. A lot of people are applying this and saying, what are the applications and services in here that want to escape, that want to get out and be their own thing? What are the tools that we need to pull out that really aren't part of the application? That should go be its own thing. It's not something that you can just snap your finger and get there, but neither is retrofitting a unit test suite or retrofitting really strong object-oriented design. All of these things are something we really have to resist in sort of like the leftist revolutionary meaning and say, okay, no, I'm not going to add another feature to this thing. We're going to start figuring out how to break this down. And it doesn't just apply at the application level, it's fractal. It applies at the module level, splitting a large application up into two concerns that still live within one application. You got users and payments, and they're two separate worlds. You have a class that's too long. Start splitting out a class, a method, etc. Another thing that is worth resisting is large tools. There are tools like, for example, Oracle, or to some people, a language like Scala or Java, that sort of force you to do big things with them. They don't want to do small things. J2EE is a great example where you have to write a ton of boilerplate code just to get started. So you, by definition, have to make a big thing in order to get anything done. You can make a big thing or make nothing. So we want to resist large tools, and I'll talk a little bit more about tools in a minute. Probably the best thing that you can start easily doing, and you can do at any point in a project, is manage your dependencies. Oftentimes, I think that software is just all about dependencies. Dependencies on gems, dependencies between classes, dependencies between methods and data. You can look at it through that microscope. But in terms of making small software and resisting large, hard-to-change software, managing your dependencies is one of your best weapons. If you can resist adding some gem that you might not necessarily need or does a lot of things, then your software might be easier to work with. if you can make it so that the dependencies between a service and your application are well defined and easily understood, then you're well on your way to having an application that less resists change. Same with your teams and processes. You want to make sure that they're dependent upon each other in the right way and in understandable ways. So another way we can move fast and make things is to use spikes. A spike is sort of like a prototype. When you're doing a spike, you're saying, hey, here's a question I have about writing some software. There's some software I need to write, but I'm not quite sure how it would go. So what you do is you constrain yourself to only tackle some part of the feature set, or you say, okay, there's this complicated thing. I'm not going to integrate with actual merchant gateways. I'll leave that off till later. So you're just trying to write the whole part of some feature or fix some bug or remove some bottleneck. But you want to go all the way through and find all the uncertainties and gotchas. And then once you're done with that spike or prototype, you can step back and take what you've learned by writing that spike and then go write actual production code or write up a plan about how to write that production code. So because you're going to be throwing this code away, one of the key constraints is time. You can only spend, like, say, a day or a few hours or some minutes or weeks on doing this. So you have to use that time wisely, which is an awesome constraint. And then you have to, once you're done, figure out how you're really going to solve it given what you've learned. So spikes are great because they help us build the right software. A ton of projects that I've been on personally were a really great idea, but they were in the wrong context. They were for the wrong scale. Like a system was designed to handle, tens of thousands of requests a second, but the real application only sees thousands of requests per second. Or something is designed for a huge organization so that you can easily change applications and deploy them instantly, but really people don't need to do that all that often. So spikes help us build the right software, find the actual requirements, and find the actual points of complication. It's easy to talk about some problem with other developers and say, oh, well, I think this will be complicated because things that I learned in the past. But that might not actually be the complicated part of the feature or the problem, whatever you're trying to do. So spikes help us go to discover what the software we should really write is. This is especially useful. There's all sorts of code or problems that I've come upon that I figure out. I think about it for hours or days just in the background in my head, and I realize that I can't solve this problem until I solve this problem. That I just don't know enough about the problem domain or the tools, and I need to just get down to business and code something to figure out what I really need to do. So spikes are great for keeping us out of the weeds. I find spikes, and especially time constraint, to be extremely useful to prevent me from fighting against some tool just out of principle, or fighting some bug just because I think I'm stupid and I should be able to figure this out. If I'm wrestling with something and I come back, if I wrestle with something for say 30 minutes and then go get a drink of water and come back and look at it, I might realize that, say, I'm using the tool wrong, or that this is really a trivial problem and I should just hack around it. So I find spikes are super useful for keeping me from going too deep into things that aren't a good use of my time. And spikes reduce uncertainty and tell us where to go. So if you're not sure what the complications are, or where the actual bottleneck is, or where the actual bug is, constraining your time is a super useful technique. And constraining your requirements, saying I'm not going to implement complete street address parsing because that's a morass of edge cases. So you can go through you're writing some shipping software, and you say, okay, I'm not going to parse all of the myriad of ways you can write a street address, but I am going to handle all the other stuff, from acquiring things from the warehouse to putting a label on it, et cetera, et cetera. So spikes help us know, I wrote a tiny trivial version of this software. Now I can write out a plan for how I would really write this software and how I would deliver the useful parts as soon as possible and make them easy to deploy and easy to code up. So really, spikes are kind of about a divide and conquer technique. You do the spike so that you can know how to take some huge project that you think is big and scary and might take a long, long time, and figure out how to reduce it into a bunch of less scary projects that you can get the benefit out of almost immediately. So leverage in tools is something I've been looking at and finding a lot of really interesting qualities. There are sizes of companies and the kinds of tools that they use, and they have different appropriatenesses. So say you're a new, you're starting up a mom and pop candle shop that's going to be in like a storefront in Grapevine, Texas. You probably don't need Hadoop, right? Hadoop is a huge tool that is really awesome when you have more data that fits in memory and you have like 20 machines laying around. But that's not useful to a mom and pop shop. For them, Microsoft Access or Microsoft Excel is a fantastic tool because they can do a lot of things with it quickly and they didn't really have to learn things. So there's every tool is a lever. We use tools because we put more energy in. We put less energy in than we get benefit out of. And it's useful to look at the languages and the tools we use in that light. So I frequently look at tools now and say, what is the cost benefit of this tool? And when do I pay those costs? Do I pay them up front? Do I pay them over time? And when do I see those benefits? Do I immediately get the awesomeness of this tool, or does the awesomeness of this tool only come over time? So for example, Postgres is very easy to set up. So I pay only a little bit of cost up front. It's very easy to define your data model, very low cost, very easy to write queries, and it works great with just a little bit of data. But something like Cassandra or Riak is relatively difficult to set up. It drastically constrains how I model my data. So there's cost in figuring out how to get my data into it. And there's cost in figuring out how do I query this effectively. And so Riak is a great tool for when you are operating at a huge scale and you can't tolerate downtime. But it's not very good for getting started because you pay such an upfront cost. So it's useful to know what is the cost benefit and is it appropriate to what I'm doing. Leverage also tells us that some tools are selfish. They want you to do a lot of work just to get them going, and there's no real benefit at all to you, to that work. Some of this is a bit subjective, but I think typing in a language is a very good example of a selfish tool. To a lot of people, telling the Java or Scala compiler what the type of every single variable is, or most variables, that's just too high cost. It takes them away from writing programs and getting them working as quickly as possible. But for some people, knowing when they've written a typo or knowing that the compiler will just outright reject incorrect programs is really useful. So tools can be selfish and it can be a little bit subjective. But again, something like Riak is a bit selfish because you have to deploy it correctly and set it up correctly before you can even use it. So it's wanting you to do more for it, and it's not giving you that much in return, at least to start. And when I've been thinking about leverage, when I look at tools, it helps me know, it's a good little reminder in the back of my head that when I'm fighting with a library or a gem or a unit testing thing or some code or Git or whatever, I sometimes step back and say, is this something I should keep doing? Should I keep using Git, or should I look for something better? I actually think Git is pretty great, but like Bazaar or Mercurial, maybe the benefit of those isn't as great as I once thought it was, and I should switch over to Git. Redis and Memcache are fantastic examples. Like if you keep using Redis and it keeps losing your data, or MongoDB keeps losing your data, then maybe you should switch to another tool. If Ruby keeps being slow and not having multi-core concurrency for you, maybe you should look at JRuby or the JVM or Erlang. It's something to keep in mind so that you can move fast, so that you can speed up. You're already using this tool, so you're moving at some speed. You want to make more things. You want to fight the tools less, so look at the leverage. Versatility is the versatility of a tool or a library or approach or whatever is a really useful thing to look at. A versatile tool makes starting off easy. So like I said, Postgres is really easy to get started with, and you pay little cost and you can just start using it. Ruby is a fantastically easy thing to get started with. You can just write shell script style programs and get started, immediately see benefit, say, okay, now I've automated this, and go off and do something else. The next step of a really great versatile tool is that you can discover the structure of your problem as you go. So if you have a small software process in your team for deploying, let's say, then as you discover weaknesses in it, you can easily amend that process. But if you have a 20-page document that describes your process, it's really hard to decide how should we change this, and and how do we change this without breaking the process such that we're making problems for ourselves. And that's why writing laws is incredibly difficult, and we have really stupid people making laws too. But Ruby, you write some shell script in Ruby, or you write a 200-line controller action in Rails. You can add structure to that as you go. As you discover where the behaviors are and where the objects are, you can say, okay, I'll pull this out and put this in something else as you go. And it doesn't require a bunch of creating new files or changing types or using an automated refactoring tool. You can just do it. It's a low effort thing to put that structure in when you discover it, and only when you discover it. You don't have to put that structure in until you're ready. And versatility means you can take one tool to start off with, grow your application, your team, your business, whatever, and then keep using that same tool to sustain that organism. So you can use Ruby, for example, to start off an application, and then as you discover what that application should do, you can keep using Ruby, and Ruby gives you other tools to structure that application. And then as you want to sustain that application, you can use Ruby in a lot of ways to parallelize the application, to grow it into separate applications, to have those applications talk to each other, etc. And the same thing for teams and businesses. If you can find some tool or some process that grows and that can grow with you and doesn't add a bunch of costs, add a bunch of busy work, then you can sustain that business or that endeavor more easily. So working faster, making more things is about working smarter, doing more of the right things, solving the right problems, resisting large software. This is, I think, the hardest thing. I think just there's something about the way people are wired that we gravitate towards large things, whether they be large teams, large companies, large software, large cars, large governments, large continents, large states, big football players, whatever. Humans seem to like big things up to some point. Use spikes as a guide. I've been doing spikes just like little programming projects on the weekend, and it's fantastic. I decide, hey, I want to try and write an analytics system. That seems really hard. Like Google Analytics is a big system. I wonder how much of I could write that in a weekend. And I constrain it down. I say, okay, I'm not going to do the charting part. I just want to see how I can get data in and query it. And I write some code, and then I write the code on Saturday and part of Sunday. I write it up on my blog, and then that's it. Maybe I come back to that code. Maybe I don't. It's no weight around my neck. I learned some things, and now if I had to actually go write an analytics program, I could do it. That feels good. High leverage tools. If you walk away with anything, please start thinking about high leverage tools. Some tools that I think are high leverage are Ruby, Redis, Rescue, Memcache, Nginx, Python, PHP. All of these tools don't require much of you to get started with, but if you're careful with them, you can go a long, long way with them. And even if you're not particularly careful, you can probably get to the point where you could pay someone who's careful to help you out. And use versatile tools. These are kind of like two sides of the same coin. Don't start with Erlang. Don't start with the JVM or Scala. Those things want a lot of you. Don't start with Oracle. Don't start with Oracle. PeopleSoft. Don't start with PeopleSoft. Use things that you can use in a lot of different ways and get a lot of benefit from, and maximize how much you learn, maximize what you learn and how you can apply that knowledge. So you want to move fast, make things, and do that for a long time. Once you find something awesome, some awesome team, some awesome application, the more you can do as a software developer to make that institution a lasting, sustainable institution is probably a good thing. And always be looking for that thing that you want to make a lasting impression with. So that is all of move fast and make things. I had originally, okay, here's the coda. I always want to do code talks, but I start working on the talks, and they end up being idea talks, like that was. But the code things are still pretty cool. Whoops. So I'm going to do a bonus track, and then I'll take questions at the end. I could have done this presentation backwards, but I'm not that fancy. Okay, so Celluloid and Metriks are two awesome, high-leverage, versatile tools for making awesomer things. Now, it happens that someone stole some of my slide deck and already talked about Celluloid. But it's okay. I'm a trained improvised actor, and I'll just make stuff up. So a little bit more about how actors work. Conceptually, these are the things that are inside an actor. You've got, say, two actors, one named Larry and one named Daryl. They each have their own thread, and then they have that mailbox, and then there's an object contained inside of it. So actually in Celluloid, when you include Celluloid into your class, it does a whole bunch of magic and makes you a really funky but powerful actor guy. So now your object has this queue inside of it. Well, now the thing that you thought was your actor you think you thought was your object is really an actor with your object inside it. So when you send it a method call, Celluloid converts it into a message, puts it in the queue, and then each thread processes all the stuff in the mailbox. So here's an example from an analytics system that I spiked out. And you can see, this is just like any other guy who calls Redis. He's going to increment a counter and fetch it out. If any of these, if record, fetch, or Redis is called, I believe Redis, then that becomes a message. So then what I can do from another actor is call methods on him. And so this is part of a network service. So this is kind of where I decode the protocol. You can have a visit, which is where you're recording a hit to a web page or whatever, and you can have stats when you want to fetch the analytics data. And you can see in here, you can, over here, I can just walk up to the code. Celluloid has a cool thing where it makes it a lot easier to name actors. So you've got an application running, and it's got all these moving parts. You can give those moving parts names. It's easier to reason about them. So I've got this Redis actor off somewhere, and that's the guy we looked at just a minute ago. So these guys are now in two separate threads. They won't interfere with each other. They can't munge each other's data. It's very nice. This is another awesome thing that Celluloid gives you. I've got this analytics collector, and it's a process that I'm running in my Unix, and it's got 3 actors inside of it. So instead of having to wire all that up by hand, in Celluloid, you can just say, okay, all of these things are in a group. They're my stats class, my Redis adapter, and my listener. I can give them names. So stats is named stats. I mean, yes, you can read. And you can tell it how to instantiate them. The other really cool thing is that borrowing from Erlang, Celluloid can supervise these actors. And if one of them should encounter an exception or something terrible and crashes, then Celluloid will start it back up. It's naive. It doesn't do anything to prevent things that just keep crashing from continuously crashing. So you have to actually watch your logs and make sure that you fix your bugs. But then it makes it also super easy to start your application. You just say, my supervision group class, just run that guy. You trap the interrupt signal so you have some way to kill it. And you call terminate on the actor group. And then you sleep your main thread and you're done. My Celluloid IO is a totally fantastic thing. Makes writing network services pretty awesome. So here's some more reading. You should read about Erlang because it's kind of the first thing that really used actors in a big way. Decel is really neat. It's Celluloid for distributed across multiple machines. If you want to dig into Ruby or concurrency in Ruby, I've written some things on my blog. And if you want to get really into it, Java Concurrency in Practice is a book with a monorail on it, which makes it awesome by default. But it's kind of it's the readable book on how to do multi-threaded concurrent programming. It turns out that the JVM has some really well thought out facilities for doing this. So it's worth going through the Java examples to really learn how multi-threaded stuff should work. All right, really quickly, I want to show you this library called Metriks. Knowing your production systems is really important, even if you're not in operations. You should know how your software works in reality, not on your laptop, but on the 30 servers or 2 servers or whatever you're running it on out in the wild where networks fail, where databases do stupid things, et cetera, et cetera. And the way to know that is not by speculating about things and not by talking about it on Hacker News. The way to know what your system does in production is to measure it and look at those numbers and then make decisions on what you should do next. So Metriks is a library that Eric Lindvall wrote so that you can really easily instrument just whatever you want in your application. So think of something like RPM or Tracealytics, except a lot more granular, a lot more do-it-yourself, but guided by you. You don't have to worry about someone else telling you what's important in your program. So the way you use metrics is you require it, and then you tell metrics, give me a counter, and I want to name it API hits. And then every time you get hit in your code on your API, you say, increment this guy. Doing it in a global variable is a little gnarly, but it's a good way to get started. You can clean it up later. The other thing that people often want to know is how long does this thing take in my program? So you can wrap a timer around some work. Say you want to know how long it takes to compute someone's rate structure, or how long it takes to create a new user when you register someone. You can measure that. The cool thing is that these compose. So a counter is sort of like one of the most basic things in metrics. A timer measures time and does some statistics on it, but it also measures counts too. So you kind of get both. And then you need to report these metrics somewhere, because numbers just sitting in memory aren't very useful. The simplest way is to just have it write out to a log file, but you can have it change the proc, the name of the process when you look at PS or top, and you can have it send to statsd or to a number of services. So the really easy way, like I said, you have it dumped to a log file. It writes, this is a metrics thing, and then it just has all of its values in a easy to parse format. So you see, this is a timer. The name of it is somewhere. Name equals stats. It does some statistics, so it gives you the 5-minute rate, the mean rate, min, max, 95th percentile. Very important. Averages lose data. An average is a useful tool, but it will tell you lies. 95th percentile says 95% of your data, your timings or whatever, are within this range. So that's useful for finding outliers where you have something that's sometimes very slow, but often very fast. Step 2, convert it to CSV. It's really easy. You just write some Ruby. This is a really good practice. If you never practice writing code, convert things to CSV. It's easy. Then step 3, spreadsheets. Who doesn't love spreadsheets? Spreadsheets are really, really boring, actually. But they're really great low-cost analytics tools. You just bang that thing into a spreadsheet, select 2 columns, and say, make me a graph. You don't have to learn JavaScript. You don't have to stand up some service. You don't have to pay for anything. You just pay for the spreadsheet. But you just go. It's awesome. Or if you don't want to use a spreadsheet, or if you're actually, running a service, you can use, there's dashboard services, Instrumental and Librado. These are kind of like statsd plus graphite in the sky. They're good. So if this is interesting to you, you should go read, you should look at Metriks, the original library that Coda Hale from Yammer developed. He did a presentation on this at CodeConf a couple years ago. It's called Metriks Everywhere. He talks a lot more about knowing your software in production by measuring it. It's excellent. You should either read the slides or watch the actual talk. That's it. I think I've used all of my time, so I'll be in the back if you want to ask me any questions. I welcome it. Thank you very much.